everyone, how's it going? And welcome to Community Conversations. My name is Liz and I am from the Dfinity Foundation. So the Community Conversations is an opportunity for you, the community, to hear from contributors in the internet computer ecosystem, as well as ask them questions live. So today we have software engineers Alexandra, Zapuc, and Dimitris Sarlis, who are going to give a presentation on how Canister smart contracts pay for the resources they use on the internet computer in cycles. So they will take a look at some of the design principles that were adopted and walk through various operations on the internet computer that consume cycles, including topics such as canister freezing and going over a deep dive on message execution costs. So I will turn it over to the two of them, and welcome to the show.
All right, thank you, Liz, for the introduction. I'm Dimitris. I'm gonna start this today, and Alexandra is gonna continue at some point later during the presentation. So let me go ahead and share my screen. All right, so as Liz mentioned, today we're gonna go over the mechanics of how we charge cycles for running Canister smart contracts on the internet computer. So before we actually dive into this, let's give a bit of background so that everybody is on the same page. So what are cycles? Cycles act as the computational resource we use on the internet computer, and we charge canisters for performing actions on the internet computer in cycles. Typically how this works is that your canister has a cycles balance, and every time they perform some operation or they receive a message or they execute a message, they will get charged. So in this picture here, we can see like a typical, diagram of what can happen. So an end user might send an ingress message to the canister that will probably trigger some execution on the canister itself. And that canister maybe can send a request to another canister or many canisters. And it will get eventually some response from those canisters once they process those requests. And pretty much on every part of this process, the canister will use some resource or many resources, multiple resources, and they will have to pay for that resource usage. So the way you typically get cycles is by converting ICP into cycles. Or if you're lucky, maybe you can get some free cycles from the cycles faucet that Flick maintains. One other important thing to note is that 1 trillion cycles are worth 1 SDR. So the price for that is kind of set, and that has some benefits. You can easily predict the prices of or the cost of running things on the IC, since that is pegged to that value. All right, so now that we have this basic context, we can move on to, the meat of this talk. So today we're going to cover some of the goals of charging cycles, the design principles behind the mechanics, and then we'll go through the various actions that result in your canisters being charged in cycles. And at the end, we'll close with some special topics that we've seen are interesting to people, and we've received questions in the past about them. These are freezing canisters and a deep dive on message execution, how exactly that can affect the cost of your messages. Let's go through the goals of charging cycles. So as I mentioned already, the first and foremost goal is that with cycles, you can pay for the resources that the canisters are using on the internet computer. Here, we're talking about some shared resources like CPU, RAM, disk, network. So every time the canister needs to do something with any of these resources, that puts some strain on the system. And the idea here is that, the more strain you put on the system, it should result generally in higher cost. A secondary goal here is that by adding some fee on these actions, we can actually make some DOS attacks harder and thus make the system more robust. So, for example, by adding some cost to storing data on the computer, one canister cannot easily take over the whole subnet capacity. And that's important because this way we can avoid noisy neighbor problems where a canister takes over an entire subnet and other canisters cannot really work efficiently or even at all. Now that we know some of the goals, let's look into the design principles that we used while implementing the mechanics of charging cycles. I think I guess the biggest difference, especially with other blockchains like Ethereum, is what we call the reverse gas model. So if you're familiar with Ethereum, the end user, in that case, is responsible to pay when they use a smart contract. In contrast, on the internet computer, the canister smart contracts are responsible for paying for the resources they're using. And typically this is happening by charging or pre-charging your canister with cycles so that they can actually pay for the resources they use. Another interesting point is that we usually have two parts in the cost function for any action you perform. There is a fixed cost for the basic operation. So for example, when you send a message, sending the empty message, and there's usually a variable cost, which represents the strain that you put on the system. So again, in the example of sending a message, if you send a larger message with more bytes, that would generally result in a bigger cost. The third point is this notion that we first reserve the resources or the cost, I should say, that your canister would need to pay. And then at the end, when we know exactly how much the operation costs, we can refund the excess. This is to make sure that basically every action will be paid for, and we won't have cases where we have to roll back something because the canister ended up not having enough cycles to cover the cost. All right, so a final disclaimer before we move on to looking into the operations that charge your canister or result in your canisters being charged. What you're going to hear about today is the current state of affairs, and we expect that as the community evolves and the internet computer evolves, and we learn more about the various costs and how they affect things, maybe some more operations will be charged for, and also their prices can change. Of course, if these things happen, we'll make sure that the community will get a heads up and they will know about it. All right, so the first use case that we'll go through is what happens with ingress messages that your canister might receive. So as we said, based on the reverse gas model, the canister that receives the ingress message is responsible for paying for it. The reason to pay for receiving ingress messages is to cover the cost of doing consensus on the message, which is a heavy operation on a subnet. And this induction cost of the ingress, when we add it to the input queue of the canister, again, going back to the design principles, consists of two parts: a fixed fee and then a variable fee depending on the size of the ingress message. The size we take into account here is the user controlled payloads, such as the method name or the method payload. So one can ask then, okay, what happens if a canister is spammed with a lot of ingress messages, right? That could be a bad thing and the canister can run out of cycles. So in order to protect against such cases, and specifically against malicious users who might try to do something like that, we offer the option to the canisters to filter ingress messages through a special method that they can export called canister inspect methods. So the way this works is that when the ingress message is submitted, We first do a quick check if the canister has enough cycles in its balance to cover the potential cost. If no, then we reject the message. If yes, then we check whether the canister exports this special function. If the canister doesn't export it, then we assume it's willing to accept the ingress message. If it does export it, then depending on the outcome of executing that function, the message will either be accepted or rejected. Next up is what happens when a message gets executed. So in this example, we'll go through a canister, let's call it A, and the blue bar denotes its cycle balance. So again, based on the principles, there's a fixed cost for this operation and a cost that is proportional to the number of WASM instructions that are executed. More specifically, before the execution starts, we reserve the max execution cost from the cycle balance to guarantee that the execution can happen. And at the end, any excess will be refunded back to the canister's balance. Now, the next interesting case is what happens with InterCanister codes. So when a canister calls another canister, there's two different costs that we need to consider here. One is the transmission cost, and that is paid by the caller for both the request and the response. And again, as usual, there's a fixed cost and one proportional to the number of bytes transmitted. There is also an execution cost for executing the request or response respectively, and that's covered by the executing canister. So the caller will pay for handling the response, and the callee will pay for handling the request. So let's go through this example to see in a few more details what happens. So here we have two canisters, the caller and the callee, and their initial cycles balances. Now, imagine that the caller sends a request to the callee. The caller's balance will be updated, and specifically, the request transmission cost will be deducted. That we know for sure. The max response transmission cost will be reserved because we don't know a priori the size of the response, so we just make the reservation for the worst case. And also, we reserve the max response execution cost. Now, once the callee receives the requests and processes the request, it will lose some cycles because it executed the request, and it will also produce a response going back to the caller. And when the caller receives that response and processes the response, it will receive the two refunds, specifically the one for the transmission cost of the response and the other one for the execution cost of the response. Next, we'll look at the management messages, which is kind of a special type. So on the Internet computer, there is this concept of the management canister, which is not like an actual canister, it's a virtual canister, and it's used for managing other canisters. So for example, installing code or updating the controller of your canister or starting or stopping your canister. Although this is kind of a special case of messages with respect to charging cycles, they do follow the principles that we've seen so far. Specifically, if the caller is an end user, it's an ingress message, just like another ingress message, and the target canister or the managed canister will have to pay for that, for the ingress cost. If the caller is another canister, then we're talking about an InterCanister call, and the caller will pay the transmission cost, just like another InterCanister call. The target canister will always pay for local execution, again, similar to what we've seen so far. A prominent example here is the install code, where typically users will define a pre-upgrade or post-upgrade hook to store things to stable memory and then restore them, or to initialize their canister when they first installed it. A special case here is the create canister request. This can only be called by canisters, as Ingress Messages cannot really carry cycles. And the other thing that we need to note here is that this incurs an additional flat cost. This cost is added just to make sure that there's not, like, we don't get spam of a lot of canister or creation requests. So it's a kind of a protection mechanism to make sure that someone will be very sure about creating a canister before doing so. And at this point, I would like to hand over to Alexandra so she can walk us through the rest.
Thank you, Dimitris. Let me share my screen. Sure. So, good. So do you see my screen? It's all good? Good. Right. So apart from the fees related to messages, the fees that have been specified so far, we also charge for the resources allocated to a canister, and more specifically, we charge for compute and memory allocation. However, before I explain a bit about these two types of resource allocation, I would like to highlight an important difference between the fees related to messages and these ones, the resource ones. So the fees related to messages, they can be considered in a way that they're active fees because they are only applied, so cycles are deducted from the canister balance only at the time when something is happening. So if we take a simple example like executing a message, then we charge for execution at the exact moment when the execution is happening. While for the resource allocation, we charge, so a canister will have to pay for the resource allocation the entire time, no matter what, even when the canister is idle and it's not doing anything. So this is very important because when we compute the actual charge, we take into consideration the time. So just wanted to highlight this. So going back to the two types of resource allocation that we have, the first one, compute allocation, is essentially the priority that is given to the canister when it's being scheduled for execution. And the second type of resource allocation is memory, and this it's defined, it can be defined, so this one is defined in the canister setting. It's an optional setting, and if we have this value specified, then when we compute the charge, we use the value that is set, and otherwise, which we estimate the canister memory usage based on WASP heap, stable memory, global variables, and WASP code. And here I would like to make the side note that, as Dimitris disclaimed in the beginning, the charges might change in the future. So to support that, I'll give here an example that we will be also charging for the queues of the canister when we estimate the usage. So that will be implicitly added to the charges for storage. Freezing canisters, it's an interesting concept, part of our design of the internet computer design. So if we go back to the fact that, to the idea that a canister will have to pay for the resources the entire time, so all the time, then one can already imagine that over a longer period of time, the canister balance will be slowly but surely depleted. So the canister in the canister setting provides this freezing time. And based on the freezing time, we ensure that a canister will be allowed to live for at least the amount of time specified there in seconds. And during this time, the canister will preserve its state and code. For example, if nobody during that time, if nobody is topping up the canister balance, in that case, the canister will be uninstalled. So we can ensure this behavior by reserving or blocking an amount of cycles from the canister balance. And the amount of cycles that we block, we will define it here as a freezing threshold. Basically, with this amount that is reserved for the balance of the canister, we can ensure that during the freezing time, the canister can pay for the resources. So the freezing threshold is, when it's computed, is computed based on the storage cost, compute allocation, and it's also taken into consideration the freezing time, the value defined in the settings. Here, as one can imagine, because we block this, we reserve this amount of cycles from the balance, one can imagine that the behavior of the canister can be slightly changed, because there can be situations when the canister cannot pay for normal operation because the surplus of the balance is not high enough to pay for a normal fee. So I think this is also something that you have probably seen with your canisters. So we will walk through a few scenarios and see how this freezing threshold will change the behavior. So a first scenario we have when we try to induct an ingress in the canister's queue, input queue. So we have here a canister which is considered to be frozen because the balance, as we mark it here, is very close to the freezing threshold. And the ingress is coming to the canister, but because of the ingress cost, then the ingress will be rejected. So as Dimitris has mentioned, we first check if the canister is willing and can pay for the ingress based on the induction cost. And if that's not possible, then we reject it. So this is one scenario when we have the case if the balance of the canister is too low and it cannot support both freezing threshold and the normal fee, then we have a rejection. A second scenario is when we have an active canister, so one that wants to perform a call. The balance of the canister is still above the freezing threshold, but we see that we have two possible outcomes. So on the left side, the balance of the canister is still quite close to the freezing threshold, so it cannot support the fee that comes when a call is performed. So we're talking here about the cost for transmission of the request and the reservation done for the transmission of the response and execution of the response. Compared to what we have on the right side, we see that, okay, we have some amount allocated for the freezing threshold, some amount for the execution, for the message cost. So these two accumulated will have to be at least like smaller or equal to the balance of the canister. A third example or a third scenario is when, let's say, we have two canister A and canister B. Canister B is marked as being frozen because the balance is way too close to the freezing threshold, so it has to support the freezing time. And what happens is that canister A sends a request to canister B, but this request will be rejected. The reason why is because it matches with the principle that we have presented so far. So the request will be executed by canister B. And since canister B has this freezing threshold blocked from the balance of the canister, then it cannot pay for the execution cost. Going to the fourth scenario, this is slightly different than the ones that we have presented so far. So here we have, again, two canisters. Canister A now is the one that it's frozen, and canister B is sending a response back. So before canister A has sent a request, and now is getting the response back. The canister A, the frozen one, can still process responses. And the reason why is because when the request was sent, a reservation was already done for the execution of the responses. So now canister A can execute the response, and with the response, canister A can also receive a refund. So here is what we have is the transition of the balance of canister A. So initially is this one, and it's marked as being the freezing threshold. And then with the refund on top, then the balance of canister A has increased. However, this might not be enough to unfreeze a canister, but a future, another response from different canister or same can add on top another refund or more refunds. So in this case, we can reach a situation that the canister is basically being unfrozen, and then the canister can start executing normally and just behaving normally. Here we thought about talking a bit more about message execution, just to get an understanding that some parts of the code might be very expensive. So as Dimitris mentioned, for a message execution, we have a fee which is composed of a fixed fee and then a cost proportional to the number of WASM instruction executed. And what we want to show here is that in the code, some operations have a fixed amount of instruction needed for them to be executed, while others can vary depending, so can have a variable amount of instruction, and that can depend maybe on its parameter. But the idea is that this type of instruction that have a variable amount of instruction needed for the execution, they work with lots of data. And we have here two examples. So we have one normal instruction, WASM instruction, and then we have a system call, which replies to the original caller. So both of them need a fixed amount of instructions, and they don't vary. It's all the time the same. And then we have, in this example, another system call. The difference here is that based on these parameters, this will copy data from the heap to the message reply. So this operation will require more instructions for this call to be executed. So yeah, this is basically the main idea, is that some operations have extra overhead because they involve copying data from one location to another. So we want to require more instruction to execute those kind of operations that are expensive. So we're almost at the end of our presentation, and before we finish the presentation, I would like us to go through the life cycles of Canister Balance. So we have taken a very simplified examples. For some runs, you can see nothing is executed, but we took a number of 10 runs, and we want to see how the balance fluctuates during this time. So we can see that from round 1 to round 3, nothing is executed, but there is still a small drop in the balance of the canister. And the reason for this is because, as we have mentioned, we have a passive fee that is applied the entire time. And here the canister basically pays the fee for the resource allocations. So then each round, the balance is slightly dropping. In the 4th round, we receive 3 messages and we execute them. So the decrease in balance is way bigger compared to the other one, because besides the resource allocation fees, then we also pay for the execution of the message. And then for round 5, nothing is happening apart from paying for resources. In round 6, we send to request. So that's why we have a huge drop, because when we send to request, then we pay for the transmission of the request, and we reserve for the transmission of the response and execution. And then round 7 and 8, again, it's only the charge for the resource allocation that is applied here. And round 9 is an interesting outlier. So in this round, the balance has increased slightly because we have received 2 responses, and with the 2 responses, some refunds. So those refunds accumulated to the balance have increased now the balance of the canister. But then again, we see a slight drop in round 10 because of the resources that we have to pay for. So yeah, that's mostly it. And next there will be questions if you have, and we can answer. I'll stop the share so that we can see also the messages.
Great. Thank you so much, Dimitris and Alexandra, for the presentation. So we do have a couple of questions that I am happy to field to you too. And for the audience here today, if you have additional questions, make sure to drop it in chat or Q&A. So first question, do the replicas created locally for development reflect the same cycle usage as in production? For example, if I run a transaction, update canister, and or do work in the canister, and it takes 100,000 cycles in my local environment, would that be the same number of cycles for an identical operation in production on the internet computer?
Yeah, so as I said on the chat, the way or the settings that the local replica runs with actually do not result in any cycles being charged. So although the calculations happen and whatnot, like you won't see your balance getting lower, right? Now, if this is like very important to people to check, we can work towards a solution. I don't think it would be too hard. But also, I should mention that the idea is that the prices are relatively low anyway, so that you can just deploy in production and check things out, right? For a service that you just built out and you just need to do some basic testing, it should not cost you more than $1 or $2, and you can run for probably days or weeks even testing things out.
Great, thank you. So moving on to the next question, why did we choose to do a reverse gas model? And if it's so beneficial for the end user, how come other blockchain platforms like Ethereum have not adopted this model as well?
So do you want to answer, Dimitris, or?
You can go ahead.
So in some situation, we basically reserve some amount of cycles that need to pay for the cost, but we don't know exactly the amount needed until we're done. So for example, for execution or for the response, we reserve in advance and then we do the refund.
Cool.
As for the part on like comparing with other blockchains, I guess my honest answer would be, well, I don't know why they didn't do it, but I think it's clearly an advantage if, without having to get some Ethereum or ICP necessarily, you can just explore the internet computer, you can interact with the services that are out there. Yeah, I see your point. Like, it is kind of clear, I guess, advantage, but yeah, I don't know why they haven't adopted it yet. That's probably good for us, right? Means more people will come to us. So
we also got a relevant comment in the chat where a community member said there are trade-offs. One isn't perfectly better than the other. Ethereum has the ability to do this with meta transactions, and it just isn't the default easy way to pay for Ethereum computation. So next question then. If a canister runs out of cycles, do these canisters exist forever until they have been topped up again, or are some canisters removed from the network after a certain time period if they haven't been topped up? And if canisters don't expire, do they just take up space on subnets into perpetuity?
So I guess this is related to my slide about freezing threshold. So what happens there, based on this freezing time, we allow the canister to exist for that amount specified there. And we compute an estimation of how much cycles the canister would need to pay during that time. So during this time, we'll preserve the state and the code of the canister. If the canister is not topped up there by someone, then the canister will be uninstalled. So we will lose the state and the code.
Cool. Dimitris, do you have anything to add to that as well?
Maybe just to make it very clear, since the state and code are gone, basically any storage is also gone, right? So effectively only the canister ID remains, which is a very small overhead. Just to make it super clear.
Okay, thanks both. Next question. In the developer documentation, there is an area which shows a chart of certain transactions and how much they cost in cycles. Would this cost basis ever change? What is it based on?
Yeah, so I think this is where the disclaimer comes in. Yes, it is possible that these prices will change as we learn more about the network and the various operations and how they affect resources. What it's based on, I mean, it could be a long topic, probably talk on its own. But on a very high level, what we did was to create some representative workload, which is a pretty vague term. I understand that, but we didn't really know what's a representative workload before we launched the Internet Computer. So essentially, it was a mix of what you saw, like message execution, ingress messages, InterCanister Codes, storing some number of bytes. And we measured the usage of different resources and tried to come up with a price that would essentially allow node providers to pay for the cost of this resource usage. So this is roughly how we arrived at these prices. But as I said, we used a workload that is like synthetic, not really close to reality. And the idea is that now that we do have certain services on the Internet Computer and we know better what are the representative workloads, this is something that we plan to look into again and revise and iterate on over time so that we can arrive to something that is fair for everyone.
Great. And Alexandra, did you have anything to add to that as well?
I think Dimitris covered it all.
Okay, great. So next question is related. What is the best way for projects to be able to estimate costs on the Internet Computer? And is there a way to easily compare and contrast with other platforms such as Ethereum or AWS?
Let me share again. So we have a slide as a backup for this. So let me share my screen. All right. So I think I answered that briefly on the chat as well. Unfortunately, we can't really tell you, here's like an average cost of a website or some service on the Internet Computer. The reason is that it's heavily dependent on your load. And if we don't know what exactly you expect in terms of number of ingress messages per second or crossnet messages like InterCanister codes per second, or how much data you need to store, it's hard for us to give like a very specific answer. So the best that I would recommend people is to look at the developer documentation that we have for the current list of prices. And then with these prices and what you heard about today, you should be able to understand how different actions reflect on your cycle balance. And you should be able to do something like what I've done here. It's completely like a speculative example. So if you know that you have 1,000 ingress messages per second and an average size of 100 bytes, and the average instruction consumption is 100 million, then you can put down these formulas with all the numbers that you can take from the documentation and calculate a final cost per second or per month or whatever you care about. I know that maybe this is not like the best answer we can give, but I think it's the best we have at the moment. But again, if this is, I think this is something that people really care about. So I imagine, again, as things evolve, we'll be able to provide better examples or better guidance around these matters. As for a comparison, I'm not sure if we have published anything around this, but I think if you go, for example, on AWS, you can figure out the cost that they have for uploading data or storing data, right? And then again, based on your estimates of how much you would load you would have and how much data you need to store, you can probably do some comparison between the two, like AWS and the Intercomputer.
Cool, thank you. So next question, is there a testnet for the internet computer if I'm a developer, but I don't necessarily want to deploy my canisters?
There isn't one. And I think we've taken a stance that you probably don't need it, because we expect that the prices are low enough so that you can just try things out in production, right? Production here doesn't necessarily mean, you open your service to the public, right? You can have a test version, like one canister, where you try things out. And then you can have, for example, a new canister when you're ready, or there's different ways you can do this. You can allow certain principals only to interact with your test canister first, and then open it up to the whole world, right? But as of now, we don't have special testnets for developers. So we recommend everyone to just use the production network and work on that.
Cool. So we are coming to the end of the questions. So if you guys do have a question for Dimitris and Alexandra, definitely make sure to get it in. Next question is the final question. So what developments and new features do you hope to see with canisters in the future that don't exist today?
So I can give one example, but yeah, I'm not sure how much or like if people are very interested in this. But basically, we are discussing about exposing some more metrics for canisters. So then you can use these metrics per canister, and you can use, for example, to attract more users. So just just to provide more information about what your canister is doing. I'm not sure, Dimitris, if you have something else.
Yeah, I'm not sure. I mean, the question is kind of broad, I suppose. Maybe one thing that I'm looking forward is to see what solutions people come up for, creating large scale services. We also have some ideas, but I would like to see, what the community develops around this. But yeah, I mean, one thing I can say is that there's a bunch of stuff that is coming up, and you probably have seen it like in the past few weeks with all the motion proposals that people participate and help us, figure out what we should do next. So there's certainly a lot of things coming up. Yeah, I think I'm just as excited for everything as
Cool. Thank you both. So we did get more questions after my last call. So One question, I don't understand the wallet canister. Could you please explain?
Yeah, I guess if I understand the question correctly, so the wallet, the wallet canister was introduced as a way for people to kind of control a canister that contains cycles and then can create other canisters. So if you remember when we talked about how you can create canisters, they can only be created by other canisters, right? Now, the wallet also helps you, I guess, if you have many canisters, you can manage them all through your wallet. You can easily top them up. You can easily start or stop them. But I will say that there's also other solutions that have been developed recently, and you can opt for one of those, and perhaps you don't even need the wallet anymore. So one example here would be Dunk, where you can just have cycles associated with a principal, and you can just use that to create your canisters, right? I hope that helps answer the question.
Great, thank you. And then the last question got cut off in the Q&A box, but I think what the person is trying to ask is if they want to learn more about canisters and cycles, what are the best resources to be able to dive deeper?
So I think the developer website, if I'm not mistaken, I think there we present most of the information needed to get you started and just build canisters and deploy them. And you can do that locally, so you can just experiment with them.
Great. And for those who don't know, the developer documentation can be accessed through sdk.dfinity.org. Great. So we have come to the end of our questions here. So a big thank you to Alexandra and Dimitris for this presentation, and a big shout out to the community for your excellent questions and for tuning in as always from all over the world. Thanks again, and see you at a future community conversation. Bye, everyone.